All right, this video is the first video on fluids. We'll cover density and pressure, including pressure, at a depth. And so we'll start with density. It's the ratio of an object's or a material's mass to volume. That's little m over capital V. Now, mass is typically in kilograms, and volume is typically in meters cubed for most of our problems. And so density will typically be in kilograms per meters cubed. Okay, this one. But, depending on textbook problem or whatever, you might see kilograms per liter, it's the unit of volume, or grams per centimeters cubed. That's another unit for volume there. You would think density is capital D or lowercase d, and it is not. It's actually rho. It's a Greek letter called rho, which is a kind of like a curvy, rounded P. It's not even, I don't even like that one. So it's something like this. Okay. And I'm going to keep that over here. Now, later on through the lesson, kind of revert to an old way of writing row because it's just faster for me, and I might write it, that's bad. I might write it something like this. Okay, so that's density. Uh, some conversions between volume you might be useful to know is 1 meter cubed is equal to 1,000 liters, which is equal to 1,000,000 centimeters cubed. Okay. Here's a list of various materials and their densities. Starting with water. Water is the one we'll use a lot. The density of water is 1,000 kilograms per meters cubed. Ice is less dense than water. That's why it floats. Wood, because there's various types of woods, will range between 600 and 900. And air, of course, is much less dense than water. Seawater is slightly more dense because it has salt content in there, 1,025. And these are various densities of uh, metals, different metals. And I realize here that I'm gonna erase this down here because we accidentally solved the problem already in a previous, try to record this previously. So there we go. Let's go ahead and solve an example here. A copper block has the same mass as a gold block. Of course, they're not the same volume because they're different densities. If the volume of the copper block is 0.025 meters cubed, what is the volume of the gold block? We're going to use our knowledge now of density, which is rho is equal to m over capital V. Now, we said that the mass of the copper, which I'll call M1, is equal to the mass of the gold, which I'll call M2. So gold is 2, copper is 1. If I rearrange our density equation, we get mass is equal to rho times volume, rho times V. And so the mass of the copper is equal to the density of the copper times the volume of the copper. It's equal to the density of the gold times the volume of the gold. And now we'll just write in some numbers here. So copper is 8930. The volume is 0.025. Density of gold is 19300. And we don't know the volume of the gold. So we'll just divide, multiply and divide to find the volume of the gold. And type this in the calculator. I get 0.011, call that 6. This is a volume, this is meters cubed, is the volume of the gold. Since gold is more dense, should be less volume than that one. Right. Cool. Let's come over here. So that's density. Um, this is pressure. This is like a definition of what pressure is. Pressure is like force. When you apply pressure to something, it's like applying a force, but that force is divided among some area. Okay. This is capital P. Capital P, capital F, capital A. You all know the units for force. Area is meters squared. Should know that from math class. And then pressure, though, this unit is called Pascal, or capital P, lowercase a. 1 Pascal is equal to 1 Newton divided over an area of 1 meter squared. So a Pascal is not very much force for area. It's a very small quantity. And so in a minute here, we'll go over some examples of pressures. What else? Kind of a way of thinking about this is, I use an example of like, let's say you're walking and you come across a nail, right? Or on the other hand, let's say there's a bed of nails. Let's say you have this, you're given a choice. I don't know why you would be given this choice, pretty ugly choice, or pretty bad choice to be given. It's like there's no good option. But would you rather lay your body on a bed of nails, or would you rather step on one nail, right? Of course, the answer is you would rather be on a bed of nails. And the reason is because of this. Would you rather the force of your body's weight, which is your weight, be applied over a very tiny area, um, what is that area? If we estimate it to be like a little circle, um, oh, I don't know. I kind of tried to look it up because I couldn't think of it. Yeah, it's like 1 times 10 to the negative 5 square meters. Okay. It's the point of a needle. It's applying all of your weight to that much point there. It's a very high pressure, and that'll puncture your foot. Um, I've actually done that before, but I had shoes on. And it was an accident. I was stepping on some wooden planks, which, there were like a building was taken down, and there was just a bunch of wooden planks there with nails sticking out of them. And I wasn't thinking. And of course, the nail went through my shoe, did not hit my foot though. So it went through the rubber, but it didn't penetrate my foot, which is good. Now, if you lay your body flat like this, you're kind of using like the surface area of like half of your body, like your back half, which is really close to maybe say like a square, not quite a square meter, but maybe like zero point 0.5 or 0.75 square meters. Um, and so the weight of your body is distributed over a greater area, and you're feeling less pressure from each point, each nail head. So yeah, you'd rather lay on a bed of nails than step on one if you had given the choice. Let's come down here in a fluid. So let's say you're in a swimming pool. The pressure that you feel at a depth is given by this equation here. Capital P is absolute pressure. P naught, this is a P, not rho. P naught is the atmospheric pressure, which I would label over here. And rho GH, this is a rho. Rho GH is what we call the gauge pressure. It's the pressure that a gauge, like literally this person had a gauge here and they measured the pressure there. The gauge would measure rho GH. Um, but the absolute pressure is this. It's atmospheric pressure plus that rho GH pressure, that gauge pressure. That would be your absolute pressure um, at some depth, okay? And by depth, I mean here is h of 0, that's 0 depth. And as we go down here is some greater depth h as we go down here. Cool. So P is absolute pressure. That's in Pascal. P naught is the atmospheric pressure, which is in physics, we use this number 1 times 10 to the 5 or 100,000 Pascal. It's really 101,300, but in a way, not really, because as you know, it changes day to day. The air pressure does vary, but this is what's accepted, and this is what we use. So we'll use this. First row is the density of the fluid, like the water, whatever this is, this fluid, kilograms meters cubed. C is the gravitational field, and H is depth. So you could be like 1 meter deep, or you could be like 2 meters deep, or so on. Cool. So when I ask you, if I were to ask you on a question, oh, actually, no, I'll just leave it there. I guess what I was going to say was, whenever you're solving a problem, are they asking for gauge pressure or absolute pressure? And typically, but not always, we're asking about absolute pressure there. Okay, I think that's